Hi, folks. My name is John O'Reilly. Let me just get this here. I'm based in Galway, in the west of Ireland. I work remotely for a Norwegian company called Neat. It's a pleasure to be back here in New York talking to you today. So it's just a microphone, okay. The Irish accent's probably not helping either. So yeah, small bit about myself. I'm a Kotlin GDE. I've been working as a software engineer for over 30 years now, and I've been working in the Android iOS ecosystem since around 2009. So as the title suggests, we're going to talk today about a couple of key areas that I feel are contributing to the increasing convergence of native iOS and Android development. An emphasis on native here, by the way. First up, we'll cover some examples of how similar the Swift and Kotlin languages are. This isn't, of course, necessarily anything new, but it's, of course, an important element of that dynamic. But as useful as that is, what I think is more impactful, the very similar approaches we now have on iOS and Android to both UI development using Jetpack Compose and Swift UI, and more recently, the fact that we now have much the same mechanisms for managing concurrency available on both platforms. And just to also mention, somewhat in the context of both platforms using declarative UI frameworks, is I think we've converged to a large degree on the use of MVVM on both platforms, or at least unidirectional data flow type variation of it. Lastly, not something I'm going to talk about in any detail, but just to mention, I think it's interesting to note how similar Android and iOS devices have become and the closer alignment of UX patterns. So the usual quick poll, I'm assuming mostly Android developers here, but anyone here doing iOS development? Okay, not too bad. And most of you using Swift UI? And lastly, anyone using Swift 5.5 concurrency functionality yet? Okay, a couple. It's funny, I gave a version of this talk at Swift Heroes in Turin a few months ago, and obviously the questions were flipped around the other way around. And one brave soul admitted he was an Android developer there. So okay, just want to show at some point some of the key milestones that have brought us to where we are today. Both platforms started growing in earnest around 2008, 2009. And of course, at that point, and for a while after, we were developing apps using Java on Android and Objective-C on iOS. And these, by the way, were some of the devices we had at the time. This is the tiny, by today's standards, iPhone 3G. And this is the Android-based G1 with this funky pull-out keyboard. And needless to say, devices on both platforms, of course, have changed a lot since then and have become, as I mentioned, a lot more aligned. Fast forward to 2014, Swift is now supported on iOS, and 3 years later, Kotlin on Android. Languages, as we mentioned, are significantly more similar to each other than Java is to Objective-C. 2019 then was a key year for UI development on both platforms. Jetpack Compose was announced at Google I/O that year and formally released in 2021. Swift UI was announced then at WWDC and then released later that year. And lastly, we saw the announcement of the new Swift 5.5 concurrency functionality at WWDC 21. So just to give some brief additional background and context to some of these developments before we dive into the comparisons. This was an article written in April 2019 by Jesse Wilson from Square, talking even at that point about how Android and iOS development was converging. He was primarily basing this on similarities in the language, device UX alignment, and also mobile team organization. But within 2 months of that article, we'd see announcements of frameworks on both platforms that would have a much bigger impact on that convergence. First off, a few weeks later, we saw the announcement of Jetpack Compose at Google I/O. Then about a month after that, Swift UI was announced at WWDC. And in terms of my own interest in this area, I had at that time, as part of the Kotlin multi-platform work I was doing, been developing a native iOS application. And as someone that hadn't really been opening up Xcode that frequently for a while, I always struggled to remember again how to set up storyboards, view controllers, and table views, and so forth. I'd seen that announcement from Jetpack Compose at Google I/O, but to be honest, it was a little abstract at that stage for me. I didn't really appreciate at that point what declarative UI was all about or the impact it would have on mobile development. Watching WWDC then, saw the announcement of Swift UI. It was available in Xcode beta that evening. In the early hours of the morning, I had my first basic Swift UI app, and I finally appreciated what declarative UI offered and how intuitive it made UI development. Something down the road that would be many people's experience using Compose on Android for the first time. By the way, one interesting point worth noting as well, I think, is the different sequence in which some of these capabilities became available on each platform. On iOS, we started with declarative UI and then later added structured concurrency, whereas it's the other way around for Android. And I think this has some implications for how existing functionality has evolved on both platforms. Okay, so let's dive into some of the comparisons. Firstly, the languages themselves. So I'm not going to do an exhaustive comparison of Kotlin and Swift. Rather, I'm going to use a number of examples to illustrate how they compare. I'm going to be mostly basing these on examples from articles like this from folks in the community. So John Sundell wrote this article about different ways of iterating over Swift collections. And I thought it would be interesting to see what the Kotlin equivalent would be. So if we look at the first few examples from the article, probably won't take people too long, but at a glance can spot which is Swift and which is Kotlin. Yeah, exactly. And if we add in array declaration, it's a little clearer which is which. Differences mentioned there in the use of parentheses, let versus val, print versus println, for example, but clearly very similar other than that. A few more from that article, and again, the key thing here is how, at a minimum, Swift is at least very readable to someone that knows Kotlin and vice versa. And probably wouldn't take a developer from either platform that long to understand, to learn how to write the other. And lastly, from John's article, we see some examples of iterating over maps. And again, closer similarities here, map variable declaration aside. Okay, lastly in this section, another recent article, this time from Sarun, talking about sorting Swift arrays. And again, we see the similarities. APIs are almost identical in initial examples, and then some differences in how we set up custom comparators. And by the way, we'll see some additional comparisons of the language in the next few sections when we talk about declarative UI and structured concurrency. Okay, we're getting to what I think are the more impactful similarities we have today. Firstly, the use of declarative UI frameworks on both platforms, Swift UI on iOS and Compose on Android. Most folks here are probably somewhat familiar with Compose, but just to level set somewhat. So a common way of explaining declarative UI is in terms of the what versus the how. With declarative UI, we declare what our UI should look like in a particular state. And state is very important in that context. Any changes in state cause the appropriate parts of our UI to be re-rendered or recomposed. Another interesting implication of this approach then is that it at least encourages use of MVVM on both platforms, and typically, as mentioned, unidirectional data flow variation of it. As well as Swift UI and Compose is also the approach using the likes of React and Flutter. And as we mentioned earlier, Swift UI was released in 2019 and Compose in 2021. So I'm going to illustrate comparisons again with a few examples. So this was a tweet from Thomas Ricouard talking about a GraphQL SwiftUI sample he created using the Apollo library. I'd been using Apollo and shared Kotlin multi-platform code, so I thought it would be interesting, with Thomas's blessing, to create a Compose and SwiftUI version of the project that consumed that shared code. These are iOS and Android screenshots from the sample. And we're going to drill down and compare, for example, how a row in that list would be represented in SwiftUI and Compose. So at a glance, we firstly see that SwiftUI uses structs, and Kotlin uses, or Compose uses Kotlin. Sorry, let me try again. Whereas Compose uses Kotlin functions. But if we ignore the outer, what you might call wrapping around the UI elements, I think we see more clearly how similar these are. Some differences, of course, like H-stack, V-stack in SwiftUI versus row column in Compose. We have async image in both SwiftUI and Compose, display an image from a URL. There's text elements in both, with some differences in terms of how styles, etc., are applied. But again, key thing here is how closely the concepts align and how easy it's becoming for a developer to sort of translate the UI from one platform to the other. And hearing more and more examples of cases like this where teams are starting off maybe with SwiftUI and then a Compose version is done based on that, or vice versa. Another example from one of the samples I have, this time illustrates the use of Canvas on both SwiftUI and Compose. This particular sample makes use of what's called a Chip8 emulator in shared Kotlin multi-platform code. This was an instruction set used in the arcade games of the past, the likes of Space Invaders. The emulator code generates an array of displayed data as it runs its program, and we want to show that in our app. So we're able to use it, as I said, in Canvas on both SwiftUI and Compose, with again, very similar code used for both. Here we're iterating over that virtual display data we're getting from the emulator as it runs its program, and then using Canvas API on both platforms to update the UI. Again, small differences in the APIs used again, but with fundamentally the same approach. And one more example from another sample I have, this time Fantasy Premier League app. This is for the main football soccer league in England, again using SwiftUI and Compose. And again, we see the similarities in structure here. And in particular, if we focus in on the UI elements, some differences in the APIs used and how styles and padding, etc. are managed, but much the same other than that. In general, if we think of our UI as a tree of components, what we typically see is closer similarities for ones like this, with perhaps bigger differences then when we get to maybe, say, screen level representation in terms of, for example, navigation, but still conceptually the same approach being used. Speaking of navigation, there were some SwiftUI changes announced this year that made the approaches to navigation and a number of other areas actually more aligned than before. First up, navigation. This is a pared down example from Compose code in the People in Space sample. showing some of the key moving parts of how navigation could be managed using navhost and composable then for each destination. And this is what the SwiftUI now, this is what it looks like now in SwiftUI with the iOS 16 updates, using navigation stack and navigation destination, which maps somewhat loosely to Compose's navhost and composable. Some differences still in that Compose uses a route-based approach, whereas SwiftUI maps to destinations using a data type, the assignment type here, for example, a different handling of start default destinations. But at least with these updates, I think the approaches are certainly more closely aligned than before. Next iOS 16 updates is the addition of chart support in SwiftUI. The example on the left here is this is an example of it here on the left, sorry, and along with the example in Compose using a third-party library called QualiPlot. And also showing this here is sort of a nice segue, I think, to an interesting point about SwiftUI and Compose ecosystems. Swift Charts is provided directly by Apple, and there's an expectation in general that Apple will provide most of the libraries that a developer needs to use when developing, say, an iOS app. Whereas on Android, there's more, of course, of a tradition that many of these solutions will come from a third-party offering like this. Next up, any layout, also added in iOS 16, explained as, for example, something that enables dynamically changing the type of a layout container without destroying the state of its subviews. It's quite a mouthful. Similar then to relatively recent addition to Compose, which is movable content of. Again, similar example from the documentation where it talks about how it can be used to produce a composable that moves its content between a row and a column based on a parameter. So different syntax, but quite similar and very useful capability now available on both platforms. Another small change from iOS 16, text fields that automatically grow their content, and again brings us in line with Compose behavior. And interesting to note here, the same use of text field in both SwiftUI and Compose. Next up, showing a partially visible bottom sheet in SwiftUI, again added in iOS 16, and again providing capability that's also available in Compose. And yet another of these SwiftUI announcements from this year, this one in relation to applying text styles across a group of controls. Again, relatively small change, but again, one that allows that closer alignment. In this example, we're applying a bold text style to all elements within the VStack in SwiftUI and column in Compose. Using provide text style then in Compose to achieve the same purpose as the font weight view modifier in SwiftUI. Semantics a little different again, but same concept in both cases. One last example showing swipe to refresh functionality in SwiftUI and Compose, with latter actually provided by Compose as a companies library. Just to also point out, as in previous text style example, slightly different approach to applying behavior like this. SwiftUI uses what are called view modifiers, example refreshable here, whereas Compose tends to sort of wrap code to apply the behavior. If we go back to the previous slide, we see that there with the font weight, for example, versus the provide text style. And again, we see the same thing here with the refreshable versus swipe refresh. Interesting to note that we can use the same declarative approach for developing watch devices in both Android and iOS. The Compose for Wear example on the left was contributed to the People in Space sample, and on the right we see watchOS version based on SwiftUI, also contributed to the same project, and again similarities in the approach being used. And lastly, in this section, I thought it was interesting to point out that not only do we now have the same, we have support for widgets on both platforms, but we can again use the same declarative UI approach for developing both of them. Next up, concurrency. And more specifically, we're talking about the structured concurrency capabilities that we now have available on both platforms. This is a really powerful capability that allows us to write async code that's easy to read. It also allows a more deterministic structured approach to error handling and cancellation, for example. A key enabler of this is the ability to have code that can be suspended and resumed at particular points. And as we'll see in a moment, Swift supports these capabilities now through the likes of tasks, async functions, and async sequence. And Kotlin, of course, similarly through coroutines, suspend functions, and flow. This approach, for example, allows executing async functions both sequentially and in parallel. I'm going to show some examples of both shortly, along with some examples of the use of async sequence and flow. And a very important aspect of this is how invocation of code like this can be tied into the UI lifecycle, thus allowing, for example, automatic cancellation when the UI is no longer shown. Just to also mention at this point that the new Swift concurrency capabilities we're talking about here were included in Swift 5.5 that was announced at WWDC last year. So firstly, let's look at an example of executing async functions sequentially using a slightly adapted version of example from Paul Hutz's excellent series of articles on Swift concurrency. Here we have three async functions, Swift async functions: fetch weather history, calculate average temp, and process weather, which itself is an async function. Some of these functions would, for example, make a remote API request and have to wait for the response. And this is the Kotlin equivalent. We see here the use of suspend keyword in Kotlin versus async in Swift, again, both denoting a function in which suspension can occur. And also the fact that we explicitly use await in Swift, whereas suspend functions can be called directly from the appropriate context in Kotlin. Looking then at some examples of how we could invoke async code like this, again, using Paul's example as a basis, can be invoked from a main function as shown here, marked again as async in Swift and suspend in Kotlin. We can also create a specific task in Swift, and similarly in Kotlin, create a coroutine from which it can be invoked. Where things get interesting then, I think, is how this can be tied into our UI lifecycle, along importantly then with automatic cancellation when the UI is no longer shown as mentioned before. We use the task view modifier in Swift UI for this, and can also, for example, use launch defect in compose, and we'll see another example of this later. Also interesting to note that we can change this behavior on both platforms here, such that the code will be invoked when a particular key changes, for example. Whereas the previous example showed how we can invoke async functions sequentially, Donnie's article about use of Swift's async let, an associated example, shows how to invoke async functions concurrently. This is again a slightly modified version from the sample and shows how we can kick off a number of tasks that will run concurrently and wait for them to complete. And we'll see this in a bit more detail in the next slides. And again, this is the Kotlin equivalent. And if we break it down a bit more, we again see the use of async in Swift and suspend in Kotlin. Very similar mechanisms then for invoking these async functions in parallel, using async let in Swift and async coroutine builder in Kotlin, and then waiting for them to complete, using await in Swift and await all in Kotlin. In this case, we're going to load a list of movies and user info and wait for them to finish. And these requests, as I said, will execute in parallel. And finally, we kick off a number of other async tasks and again execute in parallel, and again wait until they're complete. The other major component of new Swift concurrency functionality is async sequence, and that allows asynchronous iteration over a stream of values. And this is something that maps very closely, of course, to a Kotlin flow. Shown on the left here, for example, are some basic examples adapted again from Paul Hudson's articles of use of async sequence in Swift. And I've added then similar examples of the use of flow in Kotlin. We use for await in Swift to iterate over the values, and use collect in Kotlin, of course, to do the same thing. And then also a few examples of some of the operators supported. Firstly, using map to convert each value to a separate case version, and again, iterating over the result. And then filter to, for example, filter on a particular string. And again, very similar manner. So as I was preparing this section of the talk, I'm particularly looking at ways in which Swift async sequence operators compare to those supported by Kotlin Flow. I read a few articles like this talking about aspects of the Swift combined framework that were still missing from async sequence. At that time, there was still a gap that meant that in some cases, people still needed to rely on combine or libraries like this async extensions here that mimic some of the functionality provided. So I was, of course, interested in seeing the Swift's async algorithms package announced. And with this, we now effectively have even closer mapping between the capabilities of Swift async sequence and Kotlin Flow and the operators they support. And this is a few examples of some of the new operators included in that Swift async algorithms package, along with their Kotlin equivalent. Using new async method to provide that package to convert a Swift array to an async sequence, with asFlow being used in Kotlin to achieve the same purpose. And as before, we use for await in Swift and collect in Kotlin, showing example, firstly, of merge, and then zip here, and several other operators in common now as well. Just to finish off this section, I want to show one other example of how we're now talking about very similar concepts on both platforms, using in many cases the same vocabulary. I watched the session at the bottom right at KotlinConf in 2019, where Florina and Manuel talked about how cancellation of coroutines needs to be cooperative. I thought it was interesting then to see the structured concurrency talk at WWDC 21 talk about the same concepts, talking about cooperative cancellation of tasks in the Swift case. I'm going to just talk very briefly about Kotlin multi-platform, as it's something that I think can nicely complement some of the developments we're talking here, again in the context of developing native applications and in relation to sharing non-UI code. Subtitle here, obviously not the official one, but phrasing it like this to perhaps emphasize where this potentially fits in. And bringing Kotlin multi-platform up here as well, as we'll see a small example in a while of some of the similarities we've been discussing here. And they make the consumption of shared Kotlin code, including async-related code, pretty seamless in Swift. And a key concept in Kotlin multi-platform that's of interest to us here is Kotlin native. It provides a capability to compile native Kotlin code natively using, for example, LLVM on iOS. Typically, a framework is created which can be consumed directly in Xcode. And very importantly, we can access native APIs directly from the shared code if needed. And last point here is something I'm doing in a few examples, which is using a nice capability to build shared code as a Swift package and add to Xcode project like any other library. This is something Nate talked about in some detail in the earlier talk today. And just showing how the Kotlin and Swift types are mapped to each other when using Kotlin multi-platform like this. So I'm not going to go through these in any detail, but just to give a flavor, and we might see some of these, or we also will see some of these in a number of examples in the talk. The previous slide also somewhat of a segue to mention a number of interesting developments around the use of KSP and Kotlin compiler plugins for generating code, as Thaddeus will be talking about later today, that provide another way of providing necessary mappings between Kotlin and Swift when using KMP. We'll also talk about another library shortly that takes the same approach. Okay, we're going to finish up with a small example that illustrates, again, some of the concepts we've been discussing. This is based on another sample I have in GitHub called Bike Share. That sample includes broader functionality, but for illustration purposes here, we're going to focus in on showing lists of what are called bike stations for a particular bike network, this one for the case of bike sharing network here in New York. And this is what the high-level architecture might look like for an application like this. We're building a native iOS and Android app using Xcode for iOS and Android Studio for Android, using SwiftUI on iOS and Compose on Android and MVVM on both. We then, in this example, have a shared Kotlin repository, which we're consuming on both platforms. And this is an excerpt from that shared repository that we're going to use in this example. Pose for info for a particular bike network and exposes that as a Kotlin flow, something we'll use directly in our Android client, but we'll map to an async sequence in our Swift iOS client. And by the way, we're mapping from that flow to an async sequence using the really nice KMP native coroutines library that I'd strongly recommend any folks working on Kotlin multi-platform to take a look at. It supports new Swift 5.5 concurrency functionality along with a number of other frameworks. So firstly, this is what a view model might look like for this example. Typically, it's seen as its purpose as a container of observable state, changes to which will cause our UI to be re-rendered, and as a sort of a conduit to actions that were taken from UI that would cause that state to be updated. It can also be used for transforming state we get from other parts of the code to something more suitable for the UI, but although not doing that in this basic example. The pattern here for iOS is pretty common, using observable object protocol along with the published property wrapper. On Android, we're using AEC view model and also using Compose's mutable state of here to represent the observable state that we're exposing from the view model. Not too important in this context, but common enough, of course, to use something like stateflow here as well as map to a specific UI state as mentioned. And on iOS, we have a poll network updates async function, which uses that new 408 mechanism in Swift, along with the use of that KMP native coroutines library that maps the Kotlin flow I showed in the previous slide into a Swift async sequence. On Android, we're doing something very similar, in this case here, consuming that flow directly, and again, using Kotlin flow collect instead of that 408 we use in Swift. On both platforms, we're also triggering when we get new data, update of some state that would cause SwiftUI and Compose to re-render the appropriate parts of the UI. And this is what some of the SwiftUI and Compose code looks like in this example. Again, we're using Swift struct for SwiftUI and a Kotlin function for Compose, using list in one and lazy column in the other to iterate over the list of stations coming from our view model in both cases. We use the task view modifier in SwiftUI to invoke the poll network updates async function in our iOS view model, and use launch effect and Compose to effectively do the same thing on Android. And importantly to note that these will automatically get canceled when our view disappears, and that cancellation also gets propagated to the flow in the shared code. Before we show the SwiftUI and Compose code for the rows themselves, just to recap on what we're trying to show here, we have a row with a tinted image representing how many bikes are available, and then a column representing the name of the station and availability info. This is what the SwiftUI code looks for that. A lot to unpack here. We'll show Compose equivalent next, and then show a trimmed down version side by side to make the comparison clear. And here we can hopefully see the general structure at least, with the image showing the tinted icon, color based on number of free bikes, and then SwiftUI H-stack text elements. This, by the way, is from sampling GitHub if folks want to see this in any more detail. And this is the Compose equivalent. Again, don't worry about the details, but not at this point, but same structure as SwiftUI version. And we'll see the clear comparison in the next slide using pared down version of both. And then this is the pared down version, as mentioned. And hopefully, again, we see how the UI elements map very closely to each other. H-stack to row, V-stack to column, image, spacer, and text elements in both, with some API differences and some differences mentioned in how styles, padding, etc. are applied. In the previous slide, I took out the tinting code just to show clearer side-by-side comparison, but just showing this explicitly here, and again, something that can be done in a quite similar manner in both platforms. Okay, one final example that illustrates use of combining multiple Swift async sequences in an iOS app, one of which is in fact mapped to a Kotlin flow. First one, representing a list of players. This one, as mentioned, maps to a Kotlin flow using that KMP native coroutines library I mentioned. The other then represents a search query. And then using combine latest operator to combine them. And I think this very nicely illustrates again how seamless that consumption of a Kotlin flow and in Swift can be. So that was somewhat of a whirlwind tour of some of the key areas that I think are contributing to the increasing convergence of native iOS and Android development. And just to recap, there are of course many permutations in terms of how mobile teams are organized, depending on the company, the size of the project. But at least now I think we're seeing more possibilities for people working on both platforms and becoming more general mobile developers. We've seen similarities in language, but even more important and impactful is the common approaches we now have to both UI development and a concurrency on both iOS and Android. And complementing that, I think, is the possibility of using Kotlin multi-platform for sharing some parts of the boring non-UI code on both platforms. Thank you.